Today we're going to be talking about an ugly sounding word called stoichiometry, okay, which really all that means is it's just a big word for saying, can you follow a recipe correctly? That's really what it comes down to. Can you double a recipe? Can you make a recipe half? If you have this many eggs that are required, how many cups of flour do you need? That's really all we're asking with this section, but they do make it sound a little bit trickier than it is. But keep that in mind, take a deep breath, and realize we're just talking about recipes. We will refer back to the recipe we've talked about several times in the past, and that's this one. 1c plus 2b becomes 1b2c. Okay, and remember what this is referring to is one piece of cheese plus two pieces of bread becomes one sandwich. That's what the b2c is. So keep that in mind as we're working through, because we'll refer back to this just to touch base with the stuff that you already understand, and to connect it to, now we're working with what how chemicals come together to form substances, but it's really all the same idea. Okay, so let me hop into, where did it go? There we go. All right, so we're going to be using this down at the bottom here. There's this, down at the bottom here, there's this, this funny looking diagram. I don't necessarily love it, but on the other hand, we're going to work through it, and you'll see that this has kind of all of the answers that you could possibly need to be able to solve any type of problem that's thrown at you. Okay, now I personally prefer, rather than having training wheels like this, to think. And so I'm going to be encouraging you to think, because once you can understand it, then you don't need the training wheels. Then you're much more versatile in your thinking. But initially, something like this can help out as you're working through your problems. So on this page, you can see a little bit of a definition of stoichiometry, but really, we're going to just stick with the definition we mentioned. In a recipe, there are different ratios. If you want to make 10 cupcakes, how many cups of flours do you need? You'll need to look at the ratio in your recipe to figure out how many cups of flours you need for how many cupcakes you're going to make. The only difference with stoichiometry is that rather than always just starting at cups, they might start with grams. So you might have to first convert grams to cups, and then cups to cupcakes, and then maybe even cupcakes to grams. And that's kind of the types of steps you go through. So you can see here, it says stoichiometry has been frustrating chemistry students since 1972, or I'm sorry, 1792. I read that totally backwards. 1792, so quite a long time. All right, so you're going to be using this chart as we go through. This will work through, and you'll be able to figure it out. A lot of this stuff you can figure out just by looking at the chart without me even talking about it. So hopefully it'll be helpful. Okay. So the first part of it, you can see here, you've already seen some of this where it says the mass of A by using the molar mass of A. And when they say A, they're just talking about substance A. Then you can convert between the mass of A and the moles of A. Okay, so you can see here, convert 5.23 grams of H2O to moles, or convert 0.84 moles of H2O to grams. I'm going to just do one of those problems just so we see how to do it. And then I'm going to leave the other one to you. And so what we're doing here is we are just taking 5.23, try that again, 23 grams of H2O, and we are converting it into moles. And we're going to use the molar mass as we have seen before. And then the key is, guys, is that you want to have it so that you cancel out what you don't want and you get what you do want. That helps you to clarify whether you need to divide or multiply. Hopefully it makes sense that in this case, if we have a certain number of grams, we're trying to convert into moles, we're going to be dividing by our molar mass, because our molar mass is how many grams per mole. In this case, I've kind of already added it up here. It comes out to be 18.02 grams per mole is our molar mass for H2O. So we put that on the bottom, 18.02 grams for every 1 mole. And then we do the math, and our answer is 0.290 moles. You might wonder why I put that 0 on the end. It's because we had these 3 significant figures at the start, so we should have 3 numbers here in our answer. I know we haven't done too much around significant figures, but that's how you do that problem. Just to tell you how we do this next one, I'm just going to show you the setup on it, and I'm going to have you finish it, and we'll see that in your notes as you get that done. So we put 0.84 moles. Oh, by the way, look at this cancellation. Always show that cancellation. That's to make sure that you did things right. We start out with 0.84 moles, and then in this case, we're putting grams on the top. So we're putting 18.02 grams for every 1 mole. This makes sense because we've got a little bit less than a mole. We're wondering how many grams that is. So obviously we're going to get something a little bit less than 18, and our answer comes out to be. Actually, I'm going to hold off on the answer. I'll let you guys answer that, but just make sure that you cancel your moles as you're doing that. Okay, now on to the next part where we talk about how we put this together with the new information. Okay, so now this is also something that you already know, and I probably am not going to go through all of these examples because you guys have done these and you've had a lot of practice on them. So what I'll probably do is go through and do some of these in the key just to help you catch up on them. But hopefully you remember that when you convert from particles, and when we say particles, we're talking about either atoms, molecules, particles, or formula units. Those are kind of the 4 words you're looking for. But when we go from particles to moles, we're going to be dividing by 6.02 times by 10 to the 23rd, just like it says here. If we're converting from moles to molecules, which is another version of particles, that's the other direction, then we're multiplying by 6.02 times by 10 to the 23rd. So hopefully those are all familiar. You've seen them before. And one other that you've seen before. Oh, and actually, yeah, we'll just mention this. If you want to, you can also go from in this case, the number of molecules. So you're starting right here at this airport in a sense, but you can't get a direct flight to mass. You have to go through moles. Okay, so you go from particles of A to moles of A. When we say A, we just mean substance A, and then we have to go to mass. So in this case, if we have 1.2 times by 10 to the 21st molecules, we're going to go from molecules to moles. That means we're going to divide by 6.02 times by 10 to the 23rd. And then from there, we're going to multiply that by the molar mass of H2O to get the total mass of those particles. Okay, on this one, it's just the opposite. We start at this airport, mass of A, and end up at particles of A, have to go through moles on our route. There's no direct route from mass to particles. So that's kind of the idea of how to use this. And again, I'm not going through showing you how to do each problem because we're going to spend some more time working out the new problems. These ones are review, and you've had a good amount of practice on these, and you should be able to review the key that we've provided on the Google Classroom. Okay, now the last one is, of course, going from volume to moles. We've talked about this, 22.4 liters per mole. Make sure, of course, this is only when it's standard temperature and pressure. So in other words, if the temperature rises above 0 degrees Celsius, then it's going to be a different volume. But at 0 degrees Celsius, pressure of 1 atmosphere, which is the pressure at sea level, then any gas, doesn't matter what the gas is, it's always going to be 22.4 liters. So you can use this nice little conversion factor. You can flip it one way or the other, depending on what direction you're going. And in this case, we've got 2.6 liters of CO2 to moles. All we do is take 2.6 liters, we divide by 22.4, and we realize that 2.6 liters is going to be about 1/10 of a mole, just slightly more than that. The other way around, we've got 0.632 moles, and we got to convert that to volume. We're going to be multiplying by 22.4. Okay. Now, one thing to make note of, I find on the division, a lot of students, they always think I've got to divide the bigger number by the smaller number. In chemistry, that's not necessarily true at all. You want to just keep in mind, just keep thinking about what is going to make sense. Okay. If we have a certain number of liters, we're trying to convert to moles, then we're dividing by liters. So the better way to think about it is if you're going to be dividing, divide in a way that cancels out the units you want to get rid of. You're left with the units you want to be left with. That's kind of the key. That'll help to remind you. I always find, though, if you step back and you think about it like 22.4 liters for every balloon or something like that, then you can say, oh, if I've got 80 liters, how many balloons do I have? Well, 80 divided by 22.4, you know it's a division problem, and that helps to keep things clear. So think of a simple example, and that'll help you to clarify whether you're dividing or multiplying, and then apply that same principle, that same operation to the more complex looking numbers. Okay. All right, so then you can just see here, guys, that you can combine any of these. As you've seen in past assignments, you can combine any of these, and you can go from one airport to the other. You can go from particles of A to mass of A. You can go from volume of A to particles of A, but always make sure that you go through this mole hub. So you got to always convert to moles first, Then from there, you can go to any one that you want, okay? So we won't go through these because I think you've got these down, okay? All right. So now, stoichiometry, okay, we are going to, the key here is this, okay? All that we've been doing is we've just been doing the equivalent of, if we were talking about our cheese sandwich example, all we've done to this point is the equivalent of saying, okay, if you start with, let's say the bread is 50 grams per slice, and you might say, hey, instead of just saying, oh, you've got 3 slices, maybe the information you have is that you have 300 grams of bread. And then we've had to just take this step. We're like, oh, we've got 300 grams. Well, how many slices do we have? Okay, well, 300 grams divided by 50, we would have 6 slices. Okay, and that's really what we've been doing, going back and forth between grams and moles, or in our metaphor, grams and slices. That's kind of the same idea, where slices would be a count. Moles is also a count of how many we have. And so that's really what we've been doing. But the trick here is this. Now, in this next step, what we're doing is we're not just doing slices of bread. Now we're going to go to make the transition from, once we find out the slices of bread, we then figure out how many sandwiches we can make with that bread. And then we might even calculate the grams of those sandwiches at the end. So the key is, when it comes to stoichiometry, we're going from the ratio of one substance to the other, okay, in order to figure out, if I use this much bread, how many sandwiches can I make? Once we make that transition to where we're going from one substance to the other, according to the balanced chemical equation, then we can really call this stoichiometry. So in this case, the balanced chemical equation, you can see right here, we have to first balance this equation. Okay, here's that equation, and balancing this equation is pretty simple. All we do is we look at this, we say, oh, we've got 2 oxygens, so that means we need 2 of these. We've got 2 of these, we need 2 of these, and then we're all balanced. So we can do the thing where we go through each one and everything else, but sometimes they're pretty easy. You can just do it quickly like that. Okay, now the next thing is, after we've balanced that, then what we're going to do is we're going to notice the ratios in that balanced chemical equation. Okay, and so you can see here that the mole ratios are the coefficients from the balanced equation. So let me just tell you what that means. And this is a critical step that we have to make sure. So here's the key. When you have a balanced chemical equation, you can make ratios. Like you can say 2 moles of H2 to 2 moles of H2O. So that's one ratio you can make. You can also make a ratio that says, okay, for every 2 moles of hydrogen gas, I need 1 mole of O2. And notice these numbers right here, they align with the coefficients. Okay, so we can also make one other ratio with this. That's 1 mole of O2 for every 2 moles of H2O. Now, these ratios can be used in figuring out, if we have, for example, a certain amount of oxygen, how many moles of H2O we're going to form. That's the whole point of these. And by the way, these can also be reversed, okay? So you can flip them upside down in order to get the opposite if you need to go the other direction. It depends on what you're trying to cancel out, what you're trying to achieve. Now, just a review here, this can also relate back to our metaphor equation. Remember, two pieces of cheese plus 2 bread becomes 2 B, try that again, 1 B2C. Okay, and so you can do the same thing, and these will make sense. So for every 1 piece of cheese, you make 1 sandwich, okay? Or for every 2 pieces of bread, you make 1 sandwich, okay? Or for every 1 piece of cheese, you need 2 pieces of bread. But all these ratios is a way to relate your ingredients to each other. Okay, these are like 3 eggs per cupcake, whatever that is. And then you say, oh, but I have 6 eggs. How many cupcakes? Well, it's a 3 to say 5 ratio. So therefore, if you have 6, then you could of course have 10 cupcakes. It's that type of thing where that ratio just works out with your recipe. Okay, so now we're going to just put it all together and give some examples. So our goal is, if you look at this, our goal is to get to grams of water. and we're starting with liters, okay? So in this case, we're going to start down here at this airport, volume of A at STP. So we've got liters of hydrogen gas. But notice we want to get to mass of the water. We got liters of hydrogen gas. We want to get to mass of water. So hydrogen gas is A, water is substance B. But notice we don't have a direct flight. We have to go from liters to moles, moles of A. Then we've got to convert that with our balanced chemical equation, the ratio in it, to moles of B, and then get to the mass of B. So that's kind of our process. And what we're going to do is just get a quick photo of this, and then we will go from there and work through this problem together. Okay, here's our chemical equation, and here is our question. So our goal is to get to grams. Our starting point is liters. Okay, so let me show you how we work this out. So we start with 2.6 liters. Make this a little bit wider so it's easier to see. And let's draw a nice line under that. Nice straight line. Make it a little long. Let's put over here an equal sign. I know it's a little slanted. We're going to put an equal sign. We want to get to grams as our goal. So first of all, to get from liters to moles, you know what? One thing that I want to make sure I emphasize here is that rather than just writing liters, make sure you indicate which substance you're talking about at this point. We didn't emphasize this in the last section because we already knew which substance. We were only talking about one substance at a time. In this case, start with H2. Okay, we're starting with H2 because that's what we have in liters. Okay, and then once we convert to water, then we're going to be clear. Otherwise, it'll look very confusing if you don't include the substance with it in some way. Okay, so first of all, to go from liters to moles, we put 22.4 liters of any gas to moles of H2. Okay, so if we figure out the answer right now, we've converted liters of H2, 2.6 liters of H2, to moles of H2 because liters is going to cancel out, okay? Now, the next step is, now that we're in moles, we get to this point where we have what we call the mole-to-mole ratio. That means we look at our balanced chemical equation, we use the coefficients to decide a ratio. Again, like we said before, it's no different than saying 1 slice of cheese to 2 slices of bread. It's just that we're using substances, chemical substance, and our measurement, rather than in slices, is in moles, but they're both a count of some type. Okay, so in this case now, all we do is then we say, okay, we know we're in hydrogen right now, hydrogen gas, but we want to figure out an answer in water. Okay, so what's the ratio? Well, the ratio is 2 moles of H2O for every 2 moles of H2 gas. Okay, so now we can cancel out moles of H2 gas. Okay, and we don't have to do our calculation yet. Just kind of keep it clean and clear. Now, it is possible if you wanted to calculate each step separately, you totally could. But generally, it helps to avoid errors when you can do it kind of all in one line, just how I'm trying to do it here. And then finally, the last step here is you just need to now convert to grams. If we want to go from moles of H2O to grams of H2O, we're going to use the molar mass. Okay, we've already calculated this before, so we're just going to put that in there, 18.02 grams of H2O. Just be really clear, per 1 mole of H2O. Now we're going to cancel out moles of H2O, and now we just have to do the math. So I'm going to go ahead and do that calculation. You should do it too to make sure your calculator is working correctly for you. Okay, my answer is 2.09 grams of H2O. All right, there you go. And that's how you work through the steps. If you start with liters and have to go to grams, that's how you work through it. Now we're going to do another example that we'll work through again here in just 1 second. Okay, moving on to the next slide. Question is, how many molecules of water are produced when 14.6 grams of oxygen react with hydrogen at STP? Let's just look at our route here. We are asking about how many molecules of water are produced. So we're talking about our goal is to get to molecules of water. So molecules is particles. Remember, particles can be atoms, molecules, particles, or formula units. So we're going to be converting to this. And our starting point is grams of oxygen. So we've got 2 different substances. So we start with mass of A, which is 14.6 grams, and we're going to try to get to particles of B. Again, it's really a 3-step problem here, and we're going to work through it on our notebook. All right, let's just write this out. We've got 14.6 grams of O2, and we need to figure out how many molecules of, let me make this a little bit longer. How many molecules is our goal? Molecules of H2O. Okay, so not too bad here. All we need to do is, first of all, start with converting this into moles. And again, we're using the molar mass. Remember, for oxygen, it's going to be 16.00 times by 2. So for oxygen, it's going to be 32 grams. Remember, here's the molar mass, 32 grams per mole for oxygen, because we've got two O's. So 32 grams for every 1 mole. Okay, we cancel out. This is for O2. We cancel out grams of O2. Next, what we need to do is we need to go to the mole to mole bridge, is kind of what we call it, or use the mole to mole ratios, again, from the balanced chemical equation. So from oxygen to water is a 1 to 2 ratio. Okay, in this case, we want to put, so we've got moles of O2 is what we have right now. We want to cancel out moles of O2. So we're going to put 1 mole of O2 on the bottom. Again, these ratios are based on the coefficients. Don't confuse them with the subscripts. We've got 1 mole of O2 for every 2 moles of H2O. Okay, so now at this point, we cancel out moles of O2. And if we do a calculation right now, we're going to be calculating moles of H2O. Okay, so now let's remember what our last step is. We're trying to get to molecules. We know our answer right now is in moles if we do a calculation. So now to go to molecules, all we do, if we go back to our map, you can see this. We put in here 6.02 times by 10 to the 23rd molecules per 1 mole. Okay, so, and of course, this doesn't really matter what it is, but we'll put moles of H2O to make it really clear. And now all we have to do is the calculation, and we'll go ahead and work that out. And our answer comes out to 5.49 times by 10 to the 23rd. So that is our answer. And hopefully that makes sense that we're following the route that is required by the only routes that are available for our flights. All right. So, we have, you know what, I want to do one more, even though I know we're to the end. It's kind of funny they didn't do the most common one. And that is if we're going from grams. So I'm going to make up one more problem. Okay, here's the problem. You have 73.2 grams of O2. How many grams of H2O do you produce? And then here's what it'll often say. Assume you have excess H2 gas. Okay, so in other words, we've got enough H2 in the cupboard that it's not going to limit what we can make. Okay, so here's how we do this. If we go back, let's just look at our map really quick. So here's our map, and here's what we're doing. We're going from the mass of A, in this case, that's oxygen. We're going to convert that to moles of A. Well, let's first look at the whole thing. We're trying to go from right here, mass of A, to mass of B. But we can't just fly right over. We have to go through the pattern. So mass of A, we got to convert to moles of A using the molar mass. From moles of A to moles of B using the mole ratio from the balanced chemical equation. And then moles of B to mass of B. And you'll kind of see this is makes good sense as we work through it. Okay, and here's how we do that. We've got 73.2 grams of O2. We don't have to say of, let's just say O2. O2, and let's put a long line underneath it. We know we're going to need 3 full steps. And so the first thing we had to do, like we talked about there, we got to convert to moles. We're going to use that, use the molar mass for that. So that's going to be, for oxygen, it's going to be 32.0 grams for every 1 mole. Okay, let's just put O2 in there and O2. The more that we keep those labels in there, you're going to see it's going to help quite a bit. We're going to cancel out grams of O2. The next thing we have to do is we got to look at our mole to mole ratio to figure out how many moles of water we're going to produce for every mole of O2. So remember, we're converting 2 moles of H2O. So we put 2 H2O right here, 2 moles. Let me clarify that. 2 moles of H2O for every 1 mole of O2. Okay, and so all we do, we cancel out moles of O2. And then now if we do the calculation right now, we would have an answer in moles of H2O. But our goal is not moles of H2O, but rather grams of H2O. And so the last step is we're going to put in 18.02 grams of H2O, and that's just the molar mass from the periodic table. We add those together just like what we've done in the past for every 1 mole of H2O. And that is going to cancel out moles. And we're going to get an answer of, pause. All right, and our answer comes out to be 82.4 grams of H2O. So that is probably the most common type of problem you're going to work out, is going from grams of substance A to grams of substance B. So be very comfortable with that approach. All right, that should do it for today. You'll have a lot of practice, and so take advantage of that. And just remember, if you look back at this chart, it's going to help you work through it. Better, though, than looking at the chart is just to think through it. You're fully capable of having each of those steps make total sense to you. Have a great day. We'll see you.